Remember, equilibrium points are locations in the phase space of a particular system where all derivatives of the coordinates are zero. And so effectively what that means is that if you place any particle at one of those points, it should stay there forever because it will have no velocity and no acceleration. However, equilibria can be stable or unstable. The distinction being that a stable equilibrium point will be impervious to perturbations. If you put something at a stable equilibrium point and you nudge it a little bit, it will tend to go back to that equilibrium point. Whereas if you put your particle at an unstable equilibrium point and nudge it, it will flow away from that equilibrium point. So the typical mental model for this is a simple pendulum. When a simple pendulum is hanging downwards along the gravity direction, that is its stable equilibrium. If you nudge it a little bit, it will oscillate around that equilibrium. And if there's any damping or friction in the system, it will damp back down strictly to that equilibrium point. Versus if the pendulum is inverted and pointing straight upwards, if you nudge it, it will go very quickly away from that inverted equilibrium point. And again, if there's any damping or friction in the system, it will eventually go down to the original stable equilibrium point, pointing downwards. So we can now pose the question, are the Lagrange points stable or unstable equilibria? We're going to start our analysis for the off-axis points. We're going to perform a linear stability analysis, meaning that we are going to consider the linearization of the system. And our particular approach is going to be to consider a small displacement from one of these equilibrium points of the form alpha in the ER direction plus beta in the E theta direction, where alpha and beta are small quantities. We have our potential function, and we're going to linearize this about the Lagrange point L4 or L5, which we'll just call L sub I, for small alpha and beta. And so partial u with respect to x will have the form partial u with respect to x evaluated at L sub I plus alpha times the second partial of u in x evaluated at L sub I plus beta times the second partial in u dx dy about L sub I, and then plus all higher order terms, which we will neglect. If we evaluate this, we get this form for partial u with respect to x, and we can do the exact same thing for partial u with respect to y and get this form. We now plug these forms into our equations of motion, which you will recall were x double dot minus 2y dot is equal to negative partial u partial x, and y double dot plus 2x dot is equal to negative partial u with respect to y. And so we will set them equal to these linearizations, and we will assume the standard form of the solution for this type of system, where alpha is some constant a times e to the lambda t, and beta is some constant b times e to the lambda t. If we plug these solutions into these differential equations, we will get these two polynomial forms, which can be solved jointly to give us a fourth order polynomial in lambda of the form lambda to the fourth plus lambda squared plus 27 over 4 mu star times 1 minus mu star is equal to 0. We apply the quadratic formula and solve for lambda squared, and lambda squared must be negative 1/2 plus or minus 1/2 times the square root of 1 minus 27 mu star times quantity 1 minus mu star. So how does this help us determine the stability of the system? These lambda values are equivalent to the eigenvalues of the governing matrix of the linearized system. And as you may recall, we can establish stability of a linear system based on the eigenvalues of its governing matrix. So here's a nice diagram from this textbook by Hollis that classifies all of the various combinations of eigenvalue pairs and what they imply for the stability of the associated equilibrium point. And the punchline is, if we want an equilibrium point to be linearly stable, it has to have real values in the left-hand plane. And so we get various forms of sinks as shown here and here and here. For all other combinations, the system will be either completely unstable and you will have sources, so as shown here and here and here, or it would be marginally stable, or you can't really make any statements about it, such as when you have one eigenvalue lying exactly on 0 or with a real part at exactly 0. And so you will have systems like this and this, or you can have complex conjugates, in which case you have orbits about the equilibrium point. So things will just remain in enclosed orbits about that point in the linear system rather than flowing into it or out of it. Or you can have saddle points where you have one eigenvalue on the left-hand plane and one real part on the right-hand plane, as shown here. So if we would like our equilibrium points to be unconditionally stable, then we are looking for cases where the eigenvalues lie on the left-hand plane. However, in the case of the L4 and L5 points, we have a quadratic expression for lambda squared. If lambda squared has any imaginary component, if it is complex, then at least one of its roots will have a positive real part. And you should all convince yourself that you agree with this statement. So therefore, we require, for stability of L4 and L5, for lambda squared to be strictly real, which means that there's a restriction now on the contents of this square root. It has to be a positive quantity or equal to 0. If we solve this, we find that we impose the restriction that mu star has to be less than or equal to 1/2 minus the square root of 23 over 108, which works out to approximately 0.0385. Or in terms of the masses of the primaries, it means that we have the restriction that the smaller mass has to be less than or equal to approximately 1/25 of the larger mass. So L4 and L5 are not linearly stable for all combinations of primary masses. If you have, for example, equal mass primaries, L4 and L5 will not be stable. In terms of the solar system, the Earth and Moon have a mass ratio of about 1 to 81. And so the L4-5 Lagrange points for the Earth-Moon system are linearly stable. The Earth and Sun also have a mass ratio that's significantly less than 1 over 25. And in fact, the Sun and all major solar system bodies will have a mass ratio such that this condition holds. So in the linear analysis, at least, there are examples of stable Lagrange points. Now, the grain of salt here is that this is a strictly linear analysis. We are disregarding a lot of the real complexity of the system. And of course, we are using a very, very specific model, one where we only have 3 masses and 2 of them are in mutually circular orbits. And none of the naturally occurring bodies actually conform explicitly to that model. However, for small enough deviations from the model, the full nonlinear system still typically behaves like the linear system. More modern analysis has shown that for the fully nonlinear system, none of the Lagrange points is strictly speaking long-term stable. And so over very, very long periods of time, you will tend to have masses drift away from these Lagrange points. But we're talking about incredibly long periods of time, and we have examples in our own solar system, such as the Trojan satellites, which are collections of asteroids that have collected in the L4 and L5 Lagrange points of the 3-body system composed by the Sun and Jupiter as the 2 primaries. And we believe that they have been there for an incredibly long time. And that provides a really cool opportunity for missions to study what could potentially be primordial matter from the early solar system that is all collected in one spot and has been in one spot, co-orbiting with Jupiter for very, very long periods of time, potentially dating back to when Jupiter achieved its final orbit. We now perform the exact same linear analysis for the collinear on-axis Lagrange points. And after doing the same basic algebra and the same plugging in the same linearization, we get the system alpha double dot minus 2 beta dot is equal to alpha times the quantity 1 plus 2d, and double dot plus 2 alpha dot is equal to the quantity times 1 minus d, where we've defined a new term d that has the form 1 minus mu star over r1 cubed plus mu star over r2 cubed. We assume the exact same forms of the solutions, and we once again get a 4th order polynomial in lambda. And our result in this case is lambda squared is equal to 2d minus 1 plus or minus 1/2 the square root of d times the quantity 9d minus 8. And here we run into an issue, because once again, using the exact same reasoning, to ensure stability of these points, we need lambda squared to be strictly real, and therefore we require the contents of this square root to be strictly positive. D is a strictly positive quantity. Both of these denominators are norms of vectors cubed, and so they are strictly positive quantities. And mu star is explicitly defined to be between 0 and 1. So the numerators are also strictly positive quantities. So D is positive, and that means that we need 9D to be greater than 8. Except we also need everything to end up in the left-hand plane. And so to get negative real values, we also require d to be less than 1. And this is where the issue arises. If we look at the third order polynomial governing the locations of these on-axis Lagrange points, we find that not any of them can have that pair of conditions. None of the three L1, L2, L3 points can have a d that simultaneously satisfies the conditions of 9d greater than 8 and d less than 1. And so in the linear analysis, L1 through L3 are inherently unstable. They are typically thought of as saddle points with one eigenvalue in the left-hand plane and one eigenvalue real part in the right-hand plane. However, it is possible for us to find initial conditions that produce stable orbits about L1 through L3, again, in the linear analysis. So let's see if we can figure those out. We're going to follow the analysis presented in Howell and Pernica, the 1985 paper. And what we're going to be looking for are strictly periodic orbits about the on-axis Lagrange points. We can think about these as two-body orbits in resonance with the perturbing third body. You'll recall that resonance is a small integer ratio of orbital periods. We're going to have a lot more to say about resonance later on, but for now, that is a sufficient definition. Our approach is going to be to place the origin of our rotating, sometimes called synodic reference frame, at one of our Lagrange points. And we are going to define gamma as the distance between our Lagrange point and M2. So this distance will be gamma. For L2, gamma is positive, and for L1 and L3, gamma is negative. Because as you will recall, L1 lies between the two primaries, L3 lies to the other side of M1, and L2 lies to the other side of M2. We are also going to define a modified coordinate set where y prime is the same as our original y, z prime is the same as our original z, but x prime is given by x minus the quantity 1 minus mu star plus gamma. So we are just shifting our coordinate system over. Plugging this into our linearized equations of motion, we find that is x prime double dot minus 2y prime dot minus 1 plus 2c x prime is equal to 0, y double dot prime plus 2x dot prime plus c minus 1 y prime is equal to 0, and z prime double dot plus c z prime is also equal to 0. So again, these are our linearized equations of motion, linearized about a particular Lagrange point and using our displaced coordinate system. As a very quick aside, a really fascinating thing happens if you set c, the Jacobi constant, equal to 1. Let's take a very quick look at that. In the case where c is equal to 1, we exactly recover the Clohessy-Wiltshire or Euler-Hill equations for the case where the mean motion is normalized to 1, where n is equal to 1. There's a very deep connection between the analysis that we did to get to the Euler-Hill equations and the linearized analysis that we're performing here in the three-body system. We are effectively studying the same system with this linearization. And so just as we found with the Clohessy-Wiltshire equations, we have two real and two imaginary roots for the characteristic equation for in-plane motion. If the non-divergent mode of this linearized system is excited, then we will get a bounded solution. And the form of this is that is, x prime will equal negative k ay cosine lambda t plus phi, y prime will equal ay sine lambda t plus phi, z prime will equal az sine nu t plus psi. As with everything we've done in these systems, the z prime component decouples from the x and y components and can be thought of as a separate sinusoidal mode. And so it has its own periodicity and phase, and the x and y solutions are strictly coupled with the same periodicity given here by lambda and the same phase, phi, and different amplitudes given by the constants ay and k. If we have I lambda equal to j nu, where I, j are integers, then we have strictly periodic motion. In all other cases, we will get quasi-periodic motion. So what does this look like? Well, we can just go ahead and plot these solutions. And we will use this MATLAB script. We're going to plot some strictly periodic cases where lambda and nu are in small integer ratios. And then we're going to look at some quasi-periodic cases where we're setting nu to be equal to the square roots of 2, 3, 5, and 6, while lambda remains 1, 2, 3, and 4. And when we do this, here we go. So these are the first few sets of orbits, and these are known as Lissajous orbits. And these are about, theoretically, any of the on-axis Lagrange points. And in the case of the periodic motion, you see that these are strictly repeatable. And the ratio tells you basically how many loops you have. And this is, again, very, very characteristic when talking about resonances. We're going to see structures like this again and again when we return to resonances later in the course. And in the case of quasi-periodic motion, you still have boundedness to this motion. These orbits are guaranteed to stick around the Lagrange point, but they are not strictly repeating. And so you get more complex structures. But again, with the number of loops governed by the specific values of lambda and nu. Again, very, very important caveats here. This is only for the linear system. When you put in the full nonlinear dynamics, you will very quickly diverge from this, especially for larger orbits. There are very specific procedures for taking these as initial guesses, and then through the method of differential correction or other similar mathematical numerical tools, finding things that behave qualitatively the same in the full nonlinear system and in the full system that does not strictly adhere to the circular restricted three-body model. The second caveat is that these curves are being plotted explicitly in the rotating frame. This is plotted as motion about a point that is itself rotating along with the orbits of the two primaries. So in inertial space, you do not see these arcs. Instead, you see oscillations about the moving Lagrange point. But in the rotating frame, you see strictly periodic or quasi-periodic motion about that rotating point in space.